Welcome to the session. My name is Pete, and I'm a product manager on the Amazon DynamoDB team. I'm the sidebar to this presentation, here to help us stretch our mental muscles and prepare to fully absorb the rest of the content. I'm going to quickly summarize the properties of DynamoDB that make it a good choice for the purposes it is built for, and I'll touch on some patterns we see in working with large organizations who are enabling their many development teams with DynamoDB. Then I'll hand the session over to one such customer, Mercado Libre, to share their story of innovation. You might have some preconceived notions about SQL databases versus NoSQL databases, or relational versus non-relational. With so many exciting things happening in the database space at the moment, those categorizations really don't tell us very much anymore. Set them aside and let's start with an online transactional database, or OLTP, the kind you use for recording data, making controlled changes, avoiding conflicts. These are generally row-based in storage structure. You want all of those nice ACID properties: atomicity, consistency, isolation, and durability. For availability, you might expect such a database to have 3 replicas, ideally across 3 unique failure domains, or AWS availability zones. Writes and strongly consistent reads can be made from the elected leader of the replication group, or cluster, and eventually consistent reads can be served from the other replicas for better utilization and scaling. DynamoDB actually fits this description so far. There are other very interesting database designs which don't designate a leader. Amazon's early Dynamo database, as shared in an award-winning white paper, was a leaderless design. We made different choices in DynamoDB to give simple and reliable access to strongly consistent read after write, isolation via optimistic locking, and direct atomic update of individual attributes or columns in the row. DynamoDB returns a success response to your client's write request when it has durably stored your mutation in the leader and at least one of the 2 followers. Now, what happens when you want to grow beyond the capability of a single cluster? Boxes only get so big after all. The approach is generally to shard, break out the data across multiple clusters. In DynamoDB, we call each of the replica groups a partition. Most of the NoSQL or non-relational databases evolved from a desire to build this sharding pattern into the core of the database using a hashed primary key. DynamoDB follows this pattern too. Importantly, when you shard this way, you typically give up some consistency guarantees across multiple records that are in different shards. There's no single owner to maintain authority across both. Client connections need to figure out which shard to connect to for each part of the data. Often this is achieved via a proxy layer. Sometimes clients need to make multiple requests to retrieve sections of the result and then merge them. This can be complex. DynamoDB manages this for customers with a component we call Request Router. It's quite intelligent, knowing that when you make a range query that spans multiple partitions, for example, it needs to go collect the subset of results from each partition and present your client with an already merged response. Request Router is stateless and highly resilient. You don't need to think about it at all, just direct your DynamoDB client to the provided endpoint. You can imagine that managing sharded databases can be complex and operationally intensive, maybe even risky. Scale-out requirements often become one-way decisions in practice. Descaling takes too much effort and involves significant risk. And this leads us to the crux of what makes DynamoDB a good fit for its purpose. We shard early and we shard often. You could say we embrace the shard. The painful prospect of resharding the database is gone. It happens automatically in DynamoDB and seamlessly. We may even shard to the point where a single record lives on its own partition, if that's what your application traffic dictates. DynamoDB is a fully managed cloud service. There's no need to think about servers or to choose a server type based on its particular ratio of compute, I/O, and storage volume. There's also no need to think about software upgrades or engine versions. No planned maintenance in these regards. DynamoDB defines a partition, or shard, as a relatively small unit. Each partition stores up to 10 gigabytes and serves up to 3,000 requests per second. There's no need to think about managing clusters and assigning tables among the clusters, or the implications of shared clusters. You can use it for your most critical applications, the kinds of situations where an availability or latency issue directly harms your customer's experience and satisfaction. When your partition needs to grow beyond 10 gigabytes or 3,000 requests per second, it will automatically split to become two child partitions. This is completely seamless and does not consume any of the resources you need to support your application. A split can take around a half hour, but is typically much faster. DynamoDB can double your table's capability to store data and to deliver throughput approximately every half hour, with virtually no ceiling. Can your database do this? If you don't need all that storage or throughput later, no problem. You'll only pay for what you need. Scale out when you need to and scale in just as easily. Why is this important? It reduces the requirement for over-provisioning and reduces operational overhead. Sometimes it's tempting to think that we can predict the shape of our load. Maybe it has always been predictable before, but things like pandemics do happen, and scaling elasticity can be a business advantage, particularly where scaling requirements can represent an availability or level of service problem for critical business functions. A 10 gigabyte partition size keeps time to achieve a split low. It also means that if one replica of the partition suffers an infrastructure level failure, it is quickly replaced and full resilience is restored. If you're operating a database with a 5 terabyte shard size and locally attached storage, how long does it take to replace a node and restore full resilience? If a shard replica needs to be replaced, or perhaps a new leader needs to be quickly elected, what portion of your overall data is affected? We serve petabyte scale tables in DynamoDB with throughput up to millions of requests per second. Consider the blast radius reducing effect of a table which has 100,000 partitions or more. So we're seeing that DynamoDB properties include high availability, scaling elasticity, zero maintenance, low operational load, ACID properties at a per item level. What else do we need to know to characterize DynamoDB? First, it provides schema flexibility. We enforce schema only for the key attributes, allowing you the ability to easily adapt data as application requirements change. You can store as simple attributes or nested document style attributes. Another priority for DynamoDB is consistent low latency. We ask that you store and index data in such a way that it is very efficient to retrieve without a complex compute requirement that would introduce latency variation with load. DynamoDB is a good choice for known access patterns. It can easily adapt to cover new patterns over time, but it is not optimized for complex analytical needs or ad hoc queries. If you have those requirements, you'll get the best possible results if you combine DynamoDB with other stores. While DynamoDB has always delivered the ACID properties at a per item level, we added support for distributed transactions in November of 2018. You can use DynamoDB's transaction support to make multi-item atomic updates with conditions, regardless of which partition or even table that the items are stored in. And we provide for idempotency of these transactional updates too, solving for a problem which can be challenging at the application level. You can also make transactionally isolated multi-item reads. If you haven't experimented with DynamoDB transactions, I encourage you to take a look at them, as they can open up solutions you may not have considered possible outside of a traditional relational database. When I started at AWS in a technical account manager role, I supported Amazon.com through their major database modernization goals. Next, I worked as a specialist solutions architect for the DynamoDB team, helping many external customers to adopt a purpose-built database strategy and reduce operational load. Along the way, I've noted some patterns that I want to share with you as context for the rest of the session. First, large organizations have many developers arranged by team around services supporting their business. As a best practice with the service-oriented approach, there's a goal to isolate data by service, and all access between services is managed by API. Sometimes this means choosing between the complexity and cost of a cluster per service, or accepting the trade-offs of running multiple service stores on a single shared cluster. This gets operationally heavy, but if you look at things through the lens of a DynamoDB table instead of some kind of self-managed clusters, it's a much simpler picture. To be a market leader, you have to remove overhead for developers and allow them to focus on the things that make a difference for your customers. It can make sense to centralize expertise and provide a platform-based approach, which brings consistency within your own development culture. I'm now going to pass the session over to Oscar Mullen from Mercado Libre. Oscar and his team have enabled an amazing pace of innovation at Meli. I've enjoyed working with the Meli team in recent years, and it's very exciting to see the level of success they're achieving. Thanks for sharing your story, Oscar.
Thanks, Pete. Hello, everyone. Let's start with some questions to frame the story we want to discuss today. So, have you coded anything in the last couple of years? Do you have to change any core component of your application due to scale, performance, security, efficiency, or other non-functional requirement? Do you have any friction from within your organization or any stakeholder because right now we need to release this new feature or that new shiny thing, or it's not the right time to pay technical debt? Well, now imagine trying to do that same thing, but for 7,000 developers and thousands of teams at the same time across your organization. Part of the stories we will talk about today revolve around scenarios similar to those ones. For a proper introduction, my name is Oscar Mullin. I'm from Uruguay and I'm currently the IT director for Core Services, DBA, and SRE teams in Mercado Libre. These teams currently have around 2,200 engineers, and we are responsible for maintaining a big part of Mercado Libre's platform. It is a pleasure to be here with you all, and thank you for attending this session. These are some of the key takeaways we expect you can get out of the session today, so you can use them later in your organization. The first one is how to organize a platform to support 24K microservices and more than 7,000 engineers. This will frame the rest of the session. Also, how we were able to migrate 5,000 databases from Apache Cassandra to DynamoDB without asking anyone in our product organization to change a single line of code, and how we leverage the learning we got from there to also migrate some of our super critical relational databases to NoSQL models and also use DynamoDB for that. Then, once we have all of that ready, how we build an ecosystem of platform service revolving around those changes, and finally, how we were able to use the flexibility of DynamoDB to build a multi-platform service strategy. So I said I work for Mercado Libre. Mercado Libre is the largest e-commerce, FinTech, and logistic company in Latin America. To give a brief introduction from the business side in terms of metrics, we currently have more than 75 million active users distributed across 18 different countries operating on our multiple businesses. During the last quarter, our total payment value was around $17 billion, and we sold more than 245 million items. 50% of the items we ship arrive within 24 hours. So this ecosystem of businesses is comprised of several business units like FinTech, Marketplace, Logistics, Credit, Advertising, and many others. This diversity of businesses also presents significant challenge from a technical standpoint, as they require different technologies and patterns to operate and have different scale priorities. You can imagine the technology you need to efficiently run a warehouse is far different from the one you need to propose or suggest the best option for an online buyer. This also translates into large-scale technical challenges. Our platform and applications handle more than 7 million requests per minute using more than 100K instances to handle this traffic. We have more than 50,000 data services, which include databases, streaming services, data pipelines, storage services, and many others, which are being used for more than 24K microservices written in multiple languages such as Golang, Java, Python, or Node, and we have around 10,000 deploys per day. We manage 17,000 databases, and for compute, networking, and services, we have a distribution of them across 4 different clouds and our own data centers. All of this is developed and supported by 7,000 engineers. To manage this continuous growth in scale and complexity, we need to resolve many things, right? So we can make this growth sustainable and allow our organization to move as fast as possible while focusing on the different businesses we mentioned. So these things are what we think are key in order to allow this growth, and we call them capabilities. We can range them from indispensable to very mature. I'm not going to read the whole list because this is not even a taxative list, but there are three things that are key. One is security. You need to provide security-related capabilities to your organization as security threats are increasing every day. You need to provide the right abstractions to reduce complexity and allow flexibility on top of those abstractions. And also, it is important to build the standardization of mainstream components and practices to build a simple but powerful ecosystem of products. With all these capabilities in mind, we created a platform as a service that attempts to resolve these topics. Right? It also provides a common way for all our developers to run and maintain their applications in production. So here is a screenshot of our platform, which is called Fury. as you can see in the screenshot, is a comprehensive platform including quick access to all the application and team-related assets and products. You have a section for release process, you have a section for health, you have a section for operations where you can see alerting, you can manage your monitoring. You have a section for dependencies where you can see all the dependencies your code is using and whether you have to update some of those due to security or issues like that. You have a traffic section where you can see which endpoints you are publishing, which endpoints you are consuming, who is consuming what and when. You have a section for services where you can see all the core services and base platform capabilities that allow your application to run smoothly. Then you have some other sections like admin, help, quick links, and so on. Which is the journey for a developer to go from zero to production? Basically only 4 steps. You create a new application, select the language and the framework you want to use. That will automatically create for you repository, pipelines, monitoring, cost management, and so on. Then you have to create scope. For us, a scope is an auto-scaling group, for example. You just create that and Fury will automatically define which is the right infrastructure, how to handle traffic management, alerting, logs, optimizing, and so on. Then comes the complex part and also the fun part, which is writing the code. You have to write the code, and once you open a pull request, all the quality checks will be taken care of for you automatically, as well as security checks, linting, metrics, and so on. And finally, you just deploy the version that was created to production using any of the available deploy methods that we have. So one of the key things or key mantras we wanted to have is having 0 of the things on the screen in Fury. We didn't want anyone to go through a myriad of tickets, wikis, permission blockers, a lot of distributed scripts, or a person that knows everything in order to have an application in production. It's a self-service platform for all of our developers. On top of our platform, we have an interesting array of core services for our developers to use. Most of them are managed by our team, and they include different types of databases like relational databases, key value stores, time series DB, document DBs, different types of async communication tools like PubSub, calendar queues, stream, work queues, and we even have patterns as a service like event sourcing that provides a general purpose event store, event stream, and stuff like that. So if you want to implement that pattern, you don't have to resolve it yourself. One important thing here is that most of our services are multi-region, and some of them are even active multi-cloud services. This service layer, as with the platform, attempts to provide the organization with new capabilities, such as abstracted services with common interfaces and interchangeable backends, provided as a service in multi-cloud environment. The meaning of this, in the end, to explain it as simple as possible, is that most of our developers don't directly use things like SQS, DynamoDB, Elasticsearch, MongoDB, or services like that. Instead, they rely on the abstraction we create for them. And we call these things services capabilities. Which is the journey for a developer to go from 0 to having a service running in production? The first thing is selecting the service type. Once you select the service type, you have to select the criticality and metadata for that service. Automatically, we will resolve where to place that service, which high availability requirements you have, and all the security aspects around that. And then you have to create the service. We will automatically resolve authorization, authentication, provide you with code snipping, alerting, monitoring, auto-scaling, and stuff like that. So a fair question to ask is that it may seem foolish to maintain all this when we could directly empower our developers to use anything they want in the cloud or on-premise, right? We had some of these issues. While most of the scenarios in the slide could explain the reason, the one we think is most significant is organization-wide changes. With so many businesses and engineers, it is extremely hard to do cross-company tech changes without disrupting the whole organization. Imagine if for the same problem you have 100 teams using different services, you have to resolve that for every single team and align all the roadmap at the same time. So the main reasons to have our own services layer and abstraction then relies on being able to support the rapid growth of the organizations in terms of traffic, storage, and also employees, and also the rapid change in the tech industry. As new services appear and evolve, we should be able to make changes fast and as transparent as possible for our organization. Also be able to do global changes without changing the whole roadmap of the product organization and also allowing us to move and avoid vendor lock-in. For example, have a team focus on core decisions instead of distributing that decisions across the whole organization with more than 7,000 engineers, and be able to support all the different businesses with their different requirements at the same time. One other thing is important, and you may be aware of that, is that we have a lot of dynamic regulations that change constantly in different countries as tech law evolves. One of the key aspects of our service patterns is to be able to support this without having to change everyone's roadmap. By no means we aim to cut all the possible use of cloud services or even self-hosted services. We have an Off-Fury project that allows the creation of Off-Fury accounts. They will have ability to use that for sandbox experimentation. Some of our most expert teams that need to use services that are not yet available in Fury can use this also to build their architectures that they need to use these other kind of services. But this is an exception, and you need to properly justify it. So with that, we conclude the first part on how to organize a platform to support 24K microservices and more than 7,000 engineers. Now, going to the first story, one of the key things we mentioned as drivers for our services was being able to do company-wide changes with minimal disruption of the whole organization roadmap and priorities, but still make the change work for everyone, right? So we will go into what we did with our main database, our key value store. So what is key value store in the first place and why it matters to us, right? So KVS basically is one of our key databases. It stores key value store. As you can see, we are very creative with naming. It's the most used database service in Mercado Libre. It is used for the most critical applications and data. Users, orders, payment, items, shipments. From a technical standpoint, it's an abstracted database. It has an API in front of that, so we are cloud and backend agnostic. We can change engines or clouds. It relies on a proprietary SDK that was created and maintained by us, and it heavily relies on the use of change data capture features of the underlying engine. From key metric standpoint, we currently have more than 3 million requests per minute on the read and 35 million requests per minute on the write. The P99 latency is around 6 milliseconds. We have more than 4,000 developers using it every day and more than 2,400 applications using it. Right now, we have around 7,000 KVS currently active, and the uptime in September was close to 5 nines. We are supporting all of this with only 6 engineers. So how does this work? So basically, we have applications running in different clouds for Mercado Libre, and they need to use a key value store. So they talk with our KVS API, which is a wrapper on front of whichever engine we decide to use. We have some sidecars running alongside the applications. So this will handle traffic, control centralized log management and stuff like that. But basically, all requests will go to the KVS API, and then that will go to different engine or cloud provider. That is what we decide to use. Our initial setup used Apache Cassandra, managed by us, running on EC2 on AWS. So this is what it looked like. And in terms of uptime and security management, our applications talk directly to the dedicated scope of our API. As you can see there, critical applications talking to a dedicated scope of the KVS API, while non-critical applications may share some scope of KVS API. We may have some segmentation, but many applications will handle traffic with the same scope. This allows us to do more segmented rollout, control the blast radius, better management of traffic, and segment permissions. With Cassandra, this translated into the architecture I just mentioned, but also for the backend engine, we have separated clusters, and this eventually led to a situation in which we had more than 30 Cassandra clusters, each with 2 rings and each with 10 instances. As businesses kept growing in areas and traffic and storage kept increasing, this led to a situation in which complexity and management became a big problem. Some of the hard points we had, or the pain points we faced, first one was maintenance and upgrades, right? Maintenance required a lot of work with impact on the productive cluster depending on the nature of the maintenance. And also upgrading services or patching system require a lot of time invested in automation, manual process, and eventually led to some incident as well. And our Cassandra setup, due to the nature of write volume and the infrastructure we have set up, it was complex to scale up. And once we scale up, it was complex to scale down. So that led to a lot of resource underutilization, which is critical in e-commerce because as we have special events, those end up with a lot of increase in transactions. The isolation we require only made issues worse because as the number of clusters kept increasing and kept growing, this problem multiplied. And then also we have some features that were not great in our setup. The CDC wasn't great. The inability to propagate the expiration of keys through the CDC was one of those. Having only daily backups instead of 24/7 backups was another one. And also many workarounds to work with hotkeys in a proper way. Many of these things led to a lot of incidents. We have more than 10 critical incidents with our core metrics. We have many more incidents, but these were the ones that affected the most our organization. So due to the mentioned pains, we decided to look back into the market and see if there was a product that would solve our need at a reasonable cost. Initially, when we started KVS, we looked at DynamoDB, but at that point it was missing a lot of the key features we wanted, and also it was very expensive. This time around, when we reviewed, we saw that it had evolved a lot. It would resolve most of our issues, and also right now it was cost effective for us as well. So basically, in terms of analyzing pros and cons, we started with complexity. Instead of having cluster scaling, we only have to do account scaling to work around some hard limitations on the AWS account limits, but that's not a big deal. In terms of scaling itself, we have auto-scaling DynamoDB with simple downscaling and no resource underutilization versus the story that I just mentioned that it was hard to scale out and difficult to scale down. In terms of CDC, we went from having the API level CDC with no TTL support and a lot of workarounds to DynamoDB Stream, which is very straightforward and very reliable. For multi-region, setting up the whole multi-region thing with all the clusters was very complex. With DynamoDB, it's just one click and you have multi-regions. And also we can leverage the value of point-in-time recoveries instead of daily backups. So after doing this analysis in terms of features and in terms of cost, it was clear that this was the way to go. So we engaged into the process of doing all these changes without affecting the whole organization roadmap, because that was one of the premises or one of the reasons we have services. So how did this process work? So this was the setup of the Cassandra-based KVS. So any application talk to a KVS API write scope to write data into Cassandra, and then they talk with the KVS API read scope to read the data from Cassandra. And we use Amazon S3 for backups. So the first part of this migration was replicating the new data. So as data was going into Cassandra, we wanted to replicate that data to DynamoDB. So we added a synchronous step in the write, adding a little bit of latency, but we did some chaos engineering and make sure that that was not a problem for our API. So basically, any new request that was going to write something into Cassandra, first it would write something into our internal PubSub solution, and then write the value to Cassandra. This was synchronous. So that was the first part. So every new write ended up in the topic. Then we have a subscription reading that topic that would talk with the KVS API read scope of the Cassandra-based KVS and get the latest value. And then that same subscription with that value, we talked with the KVS API write scope in the DynamoDB KVS and write the data into DynamoDB. So with that, we had all the new data coming in, also going to DynamoDB. But then we have to replicate the stale data or the old data. So the night after we started the replication of the new data, we took a backup of our Cassandra cluster, and we have a historical processor that would iterate through the backup. The first step was talking to the KVS API read scope in the Dynamo-based KVS. Why that? Because if the key was already there, it meant that was written by the new data flow, so we don't have to go check, get the latest value from Cassandra and write it. It's already there from a newer process, so we don't have to do anything. If it wasn't there, we go to the KVS API read scope, Cassandra-based, get the value from the actual Cassandra, and then talk with the KVS API write scope in the DynamoDB to store that data into DynamoDB. So basically, we iterate through our historical data in Cassandra, get the latest from Cassandra, and store it back in DynamoDB. And with that, we have both flows, right? The new data and the old data flow. We use optimistic locking to avoid issues or conflicts. And the next step was communicating with the teams, right? When the backup process is complete and when the pulse of subscription is almost up to date, we coordinated with the team 5 to 10 minutes of planned write downtime at night, and we marked the KVS as fully migrated in the metadata. That, in the end, would trigger a DNS routing change, so the API or the Meli application was not longer talking at all with the Cassandra-based KVS API, and it was only talking to the Dynamo-based KVS API, so all reads and writes are going directly to Dynamo. However, as you know, when you make change to DNS, it could take a while to replicate in all the involved servers as you have DNS caching. So we also pointed the old KVS API Cassandra-based to DynamoDB. So if any rogue request ended up going there, we can effectively send it to DynamoDB, and we make sure that nothing else was going to Cassandra anymore. So with that, we moved away from our Cassandra setup to our DynamoDB setup without asking anyone in the organization to change a single line of code, only asking them 5 to 10 minutes of downtime to be able to complete the migration. So it is worth mentioning that our KVS API may seem like a simple wrapper or router, but it's much more than that. So at the routing layer, we have a hotkey collector that allows us to collect hotkeys before they reach the actual backend, so we can detect hotkeys coming in. And also we have a hotkey blocking feature at the controller level that will drop all the traffic for the specified keys that we want to stop the traffic from hitting, so we can cool down that specific keys. We also have Amazon Elastic Cache at the service layer. This mainly, the main reason why we use Elastic Cache here is because many different businesses have different requirements in terms of how many times they can hit a specific key, or even it could be very costly to send all the traffic to Amazon DynamoDB because they have a lot of traffic. So we have this here to hold that, but also allow us to be still cloud agnostic and engine agnostic, as this is just a layer of cache, and we could change Dynamo for something else and we will still have the cache there, or that's one of the reasons why we don't use DAX. And finally, at the service layer, we also have the consistent multi-region sharding that basically allow us to segment in a consistent way our traffic into different regions when we use DynamoDB global tables. At the API, at the DynamoDB level, we also have scheduled boost, basically because we have a lot of businesses which peak of traffic is the norm. So we will have a lot of peak of traffic, and you know that Dynamo could take a while to scale as any other API. So basically, with the scheduled boost, teams can let us know in advance which times they will receive peak of traffic, and we will go and scale up the table for them so it's ready when they send this traffic, and then we have a job that will scale it down again. And we also have the minimizer, which is a feature we already have for our compute load that basically uses machine learning models to understand which is the right minimum for each table. So we can set that at different times through the day and save a lot of money because of that. So as you can see, our traffic grew significantly through the last years, even more with the COVID-19 lockdown. And in order to be able to cope with this traffic in a sustainable way and also with the right level of availability, our migration to DynamoDB was completely key. As we moved from having 10 incidents to only one, and also, as you saw, we have some built-in features to work smoothly with it. Just as a small disclaimer, we have nothing against Cassandra. It is a great software. We only told our journey with KVS and the experiences we have had, which may be very, very different in another context. And with that, we conclude our first story and we can move to the second one, which basically was, okay, so if we have such a great success with migrating our KVS to DynamoDB, couldn't we move some of our super critical legacy databases to KVS as well? This is an example of our payments API, right? This is the most critical API in the whole payment flow. As you can see, it talks to a relational database for all the rights. And we have some other applications that need to do some queries, complex queries to that database, so they also use that database. And as we have a lot of reads directly by the payment ID, we already have a setup in which we use the CDC of the relational database to propagate all the data to KVS, so all the reads can go to KVS, right? But remember that here the critical portion are the writes. If you cannot write the payment, you cannot process the payment. And that was relying on our relational database. Our payments kept growing year over year. We now have more than 2.6 billion transactions per year, a 114% growth year over year, more than 5,000 growth in the last 8 years. But our response time kept increasing, and that was not only the only issue. We also have some other pain points, right? Like modeling JSON as a normalized database is complex, and we have more than 15 tables involved in the creation of a single payment, which is problematic. Also, we have issues with high availability. As you know, scaling out relational databases is not simple. This is kind of changing now with the new SQL landscape, however, still true. And also, you have complex maintenance, right? You have to account for hardware, end of life, storage, replication, and when you actually have an incident on a very big relational database, coming back online is not that simple every time. So that was one of the other issues. We have issues with the complexity for our developers as they have to properly configure and manage database connection pools, and also issues with some server-side specificities. So those were mostly the main issues we have, and we saw that that was not scaling properly for what we needed. So we decided to actually move to a new NoSQL engine instead of relying on the relational database, and that started with rethinking the model, right? The first part was evaluating all the access patterns, right? As you saw, most of our reads were by key, but we also had some other access patterns, so it's important to evaluate all the data access patterns you may have. You have to resolve all of the out-of-the-box features that are provided to you by the relational database, like auto-increment, for example. You have to be able to have a rollback or fallback process because something can go wrong and you can figure out later when you see inconsistencies or stuff like that. And you have to work with the development team to redefine the domain model to use the new persistent model. This is a change you cannot do without involving your developers or the payment application development at least. Which was the process to make this migration? The first one was replicating the new data. You're going to see a lot of similarities with our migration from Cassandra to KVS. So as I showed you in the first diagram, we already have a CDC and we were reading that to replicate to a KVS for reads. Well, we leveraged that and also used that subscription to write the values into a new KVS that was going to be our source of truth. So every new payment that was going to the relational database was also being written into DynamoDB, a new KVS that will be our new source of truth. As I told you, we also have some access patterns that are not by key. So we also use our stream service to replicate that Dynamo data, the data that we write in our KVS, to our DocumentDB service, which is based on Elasticsearch. It's an internal service of Mercado Libre document search. So when they want to do complex querying that go beyond querying by key, they can talk to the Elasticsearch setup. Okay, so we have new data being replicated. Now we have to replicate the old data or the stale data. So we did an approach very similar as with Cassandra. We have a backup of the database. We have a backup replicator that was going through the backup, and for each record in the backup, it was writing that into KVS, the new KVS source of truth. So at some point, we have the new data and the old data. We also have to create this window of maintenance to be able to cut the traffic for a while and end the replication. But with that, we completed the migration. As you can see in this diagram, we are using DynamoDB global tables because that provides the level of availability we expected to have our most critical applications there. The new architecture for our payment looks more like this. We have a payment API that talks to KVS API. We use active-active region sharding, the feature I show you when segmenting our KVS API, so we can consistently write things into different regions. And then we use our stream service to collect the data that is being propagated through Amazon DynamoDB stream. And with that, we have a payment sync, which is an HTTP sync, receiving all the information that comes from the stream, writing that into the legacy database, because there are some applications that couldn't yet move to the new model, so they keep querying the old database. And we also propagate that into our document search service, which is Elasticsearch based. So the ones that already moved can consume that data from there. We move from having 7 critical incidents that affect our payments to 0 since we moved to DynamoDB and KVS. So that also shows the level of availability we were looking for, even with the increase of traffic. And with that, we complete our second story, and we can go to the third one. So, as with our businesses that I told you is an ecosystem, we believe that a lot of the value we add in the services come from the ability to build a simple but powerful ecosystem of services that simplify the life of our development team, and add a lot of value and productivity. So, cool. We now have a awesome, fast, reliable key value store service. But applications need much more than that, right? They need different data access patterns. We will have also the need for auditing, who is doing what, when, and where. We need also the ability to export data, the ability to transmit data through the organization with different channels. So we need much more than that. And you can provide that to your developers in 3 different ways, right? So you are on your own, so you can write the data to this key value store. Now it's up to you how to get it out. You can provide an intermediate interface, like, okay, here's a topic that is providing you all the reads and write from the KVS. It's up to you what you want to do with that. Or you can provide that as a service, so everything is solved for the developers, right? So we decided to go with this last option, as it maps with our philosophy of solving as much as possible from our end, so developers don't have to worry about this, and we can do this one time in an efficient and controlled way. So this is a diagram of our ecosystem. As you can see, we have KVS and we have the DynamoDB streams, and our stream service is consuming that and powering the whole ecosystem of services. For example, we can propagate the data to any HTTP sync. We can also propagate the data to our PubSub internal solution, which is called BQ. It's an active setup using Apache Pulsar on Amazon AWS and also Google PubSub on Google Cloud. We can propagate this data to the payment sync, as we saw with the payment migration, so the data can be replicated to the legacy relational database, or to our document search service that goes to Elasticsearch, as we already saw as well. It can even go to our audit service, which uses Kinesis, S3, and Athena. We can also export this to S3, so they can consume this data through our object storage setup. What it means this for developers is that if you want to write your data to KVS and then do some super complex queries on Elasticsearch, you only have to do 3 clicks and go write your data in KVS and go look for it in Elasticsearch. We take care of everything in the middle. And that is true for all the other things that I just showed you. With that, we conclude our third story, and we can go to our fourth and last story. That is how we build multiple KVS flavors. So once we had this robust KVS and also this ecosystem, we wanted to get more value out of our KVS. So we built multiple flavors of KVS. For brevity reasons, we're only going to mention three. The first one is the semi-transparent KVS segmentation. The second one is our KVS Vault. And the last one is how we added secondary index to KVS so they can do some more complex querying there as well. So what is data segmentation for us? So data segmentation is the ability to logically or physically separate data based on a certain criteria. Right? So this separation is key for many regulations in different countries where they want to have their users' data separated from other countries or their financial data separated, or even with different permissions, or even located in different places in the world. Right? But it's not only useful for compliance. It also reduces the blast radius when you have an incident or when you have fat fingering or stuff like that. It also allows for better cost allocation, for better security management, reduce performance issues, quota issues. So it's very valuable, right? Without any features for data segmentations, applications will create a single table or a single database, right? And store all the information from the different countries together. Right? This is simple for us developers. We only have one database or one table. However, it may not be compliant or it also is exposed to all the risks I just mentioned. So ideally, we would need to go to something more like this, where you have multiple different tables holding the data for different countries. Right? But this is complex, right? Much more complex than the other thing. So you need to manage multiple databases, orchestrate many tables. You have to add complexity for data locality, for example. So it's much more complex than the other setup. So basically what we built and continue building, leveraging the value of our abstraction, is a way to do this in a semi-transparent way. Right? So when you want to create a sharded KVS, the only thing you do is you say you want that separated, in this case by country, for example. And in the backend, we will have multiple different tables or databases for you. But for you, it will only look like one database, right? You will only have to handle and deal with one database. The only thing you have to do is, through our SDK, send a header saying which is the shard where you want this data to be written or read from, and that's it. We will take care of the rest. Note that we could use different AWS accounts for this. You don't have to always have the data in the same AWS account, or we can even use different regions in the world if you have specific requirements on data localization or data placement. So which are the benefits? It limits the blast radius when you have issues. You don't have to share quotas. You can adhere to regulations as they keep appearing frequently in different countries. It's very simple for end developers, and you have flexible data localization. Going to our KVS Vault, what is that? KVS Vault is an extra secure flavor of KVS that we use to storage, for example, personal identifiable information. Right? These DynamoDB tables live in isolated AWS account. They have encryption at the API level, in addition to the encryption we have at the DynamoDB level. It has restricted integration, so we can control where the data is going. And also, it has an integration with our audit service. So every write and read, we storage information about who made the read or the write, when, why, stuff like that. And it also has some other secret security measures that are not really relevant to this talk. And to complete with the last flavor, we have QKVS, which is queryable KVS. So this should be no surprise for you how to query a key value, so you can only query by key. So as you saw, if we wanted to do more complex querying, we had to go with the whole ecosystem. So you have to turn on the document search integration, and you will go look for the data in Elasticsearch. However, that was costly for us and also complex. We have to handle a lot of infrastructure. So for many document search, we saw that they were just adding an extra column. So basically, we enable and leverage the value of a secondary index in DynamoDB, and we created QKVS. So now developers can use secondary indexes, and they can do this kind of no so complex queries in our KVS as well. Which are the key benefits of this? We have to deal with less infrastructure. We have fewer point of failures. We have one single SDK. We use a familiar backend, and we already have all the integrations solved. And with that, we conclude all the things we wanted you to take away from the session. So which are then the key takeaways? The first one is Mercado Libre adding this layer of abstraction was key for flexibility and velocity. The migration to DynamoDB was absolutely key in keeping up with traffic with high availability. The process was not trivial. I show you only the nice part, but we have a lot of issues in the process we have to solve. We are far from perfect. And the fast evolution of DynamoDB made it possible. Also, DynamoDB Stream is a great enabler for service-to-service integration, and global tables provided us with the level of availability we wanted or we needed for our most critical applications. Another key takeaway is that with the right preconditions and considering scale and other things, you can definitely migrate your relational databases to a NoSQL model, and you can use DynamoDB as the storage for that. And finally, the flexibility we saw with DynamoDB allow us to create multiple abstracted services to be built on top of it. So that also adds a lot of value for our developers. So these are the key takeaways for today's sessions. I hope you have enjoyed the session and you can use some of these ideas on your own companies. Thank you very much. Looking forward to hear from you. If you have any questions, please do not hesitate to contact us. Thank you.